Fascinating near-Earth objects, NEOs, you know.
Absolutely. And specifically, how we defend our planet from them. Planetary defense.
Exactly. We've looked at a great NASA documentary, Planetary Defenders, plus some recent news and strategies.
Yeah, lots of material.
Our goal here is to give you a fast but solid understanding of this whole field. Expect some surprising stuff.
Our mission really is to unpack the process, how we find these asteroids and comets, how we track them, and what we might actually do if one's heading our way.
Showing the work behind it all.
Right, the dedication, the discoveries, the historical context, all of it.
Okay, let's start with discovery. How do we even find these things?
Yeah.
The documentary showed this real-time excitement around spotting a new PHA, a potentially hazardous asteroid.
Yeah, it's pretty cool. They basically take quick sequences of images, like 4 frames of the same patch of sky.
Like a mini-movie.
Exactly. And software flags anything that moves between those frames against the background stars. That's your potential candidate.
But it's not just automated, is it?
No, not at all. That's the interesting part. The software might flag hundreds of potential movers, but then astronomers have to actually look and verify, is it real? Or just, a satellite flare or some noise.
So human eyes are still crucial.
Definitely. Automation plus expert judgment.
And it's not just the big observatories, right? I liked how they mentioned amateur astronomers.
Oh, yeah. Their contribution is really valuable. People spending their own time scanning the skies.
Imagine finding one. Being the first person ever to see a new minor planet.
It's got to be a thrill. But for the initial wide-scale searching, the heavy lifting is done by these dedicated wide-field survey telescopes.
Constantly scanning.
Constantly. They image huge areas of the sky, and the technique is clever. They digitally remove all the known stars and galaxies from the image.
So anything left over.
That's moving and wasn't there before. That's potentially an NEO.
Okay, so that's how the initial detection happens.
Yeah.
What's the big picture takeaway from that part?
Well, it's a global effort, constantly scanning. We're doing pretty well finding the really huge ones, the civilization enders.
Over 95% found, I think the source said.
That's right. But the smaller ones, say 140 meters plus the city killers, those are much tougher. We've only found maybe 40% of those.
Okay, only 40%. That's
yeah,
a bit sobering. So what happens right after a possible detection?
Speed is key. The information, a temporary name, time, location, brightness, it gets reported almost immediately.
Where does it go?
To the Minor Planet Center. It's based at Harvard.
Oh, okay. The central hub.
Exactly. They're like the global clearinghouse for all small body observations. They collect data from everyone, everywhere. And then crucially, they make the orbital data public.
Public. So anyone can see it.
Yep. It's a very open, collaborative process, which is essential, really.
Why is that so important?
Because one observation is just, well, one point in time. You need more data to know where something's actually going.
Right, like seeing a ball for just a split second versus tracking its whole path.
Precisely. So once the Minor Planet Center puts out the initial data, other observatories jump in to get more observations. More data points mean a much, much better orbit calculation.
Which leads us to figuring out the actual threat, doesn't it?
It does. And that's where CNEOS comes in the Center for Near-Earth Object Studies at JPL, the Jet Propulsion Laboratory.
Okay, JPL. What do they do?
They take all that incoming data from the Minor Planet Center, and they calculate their refined orbits. They project these paths forward, sometimes 100 years.
100 years? Wow.
Yeah, looking for any potential close approaches or, importantly, impact risks with Earth.
And this whole cataloging effort, it was actually mandated by Congress.
That's right. First, for the big ones, a kilometer or more across those potential global catastrophes.
The ones we've mostly found.
Yes, over 95%. Then the mandate expanded down to 140 meters, still big enough to wipe out a city or cause major regional damage.
And that's where we're only at about 40% found.
Correct. So the takeaway is we've got a good handle on the giant threats, but there's a whole population of smaller but still very dangerous objects out there that we haven't found yet.
How does CNEOS keep track of all the new data constantly coming in?
They have automated systems, kind of like digital watchdogs.
Watchdogs?
Yeah, constantly scanning the data feed from the Minor Planet Center. If any new object shows even a small chance of hitting Earth,
An alert goes out?
a rapid alert, yes. And that triggers astronomers worldwide to get those vital follow-up observations immediately.
So telescopes like Spacewatch get involved then?
Exactly. They perform crucial follow-up work to refine that initial orbit, which might be a bit fuzzy at first.
They mentioned the orbital arc in the documentary.
Right. The longer you observe an object, the longer its arc across the sky, the more accurately you can predict its future path. It just tightens the uncertainties.
And they focus on virtual impactors. What are those?
Those are objects where, based on the current data, you can't completely rule out an impact, even if the probability is tiny.
So even a 1 in a million chance gets attention.
Absolutely. Because the consequences, however unlikely, would be so high you have to track them very closely until you can definitively rule out an impact.
Makes sense. Okay, so we found it, we're tracking it, but knowing just its path isn't enough, right?
No, you need to know what it is, its characteristics.
And visible light telescopes have limits.
They do, especially for really dark asteroids. Some asteroids are, blacker than coal. They don't reflect much sunlight.
Hard to see.
Very. That's why infrared telescopes are so important, especially space-based ones.
Because they detect heat.
Exactly. Asteroids absorb sunlight and radiate heat, and infrared telescopes can pick that up, even from dark objects.
And there's a new mission coming for that. NEO surveyor?
Yes, NEO surveyor will operate in the infrared from space. It should give us a much better inventory of these darker, harder-to-spot asteroids.
The documentary also brought up that comet hitting Jupiter, Shoemaker-Levy 9.
Ah, yes, back in 1994. That was a huge wake-up call, seeing those impacts happen live, basically.
What was the impact of? Well, impact.
It really drove home that these collisions